So we have 2487 of LeetCode removing node from the linked list. And the question says that you are given the head of the linked list. Remove every node that has a greater value to the right of it. So basically you start from the head, and if you find a greater value, remove all the node smaller than it, right? You are at let's say 3 and you found 8 after that, so remove 3. Basically you have to return 13 and 8. Now before solving this problem, let's look at the time constraints we given. The number of node in a given linked list of the range 1 to 10 raised to the power 5. Now we need to figure out the worst time complexity that we can have. Let's say in a question the number of node is 10 raised to the power 5, right? So O of n operation will be O of 10 raised to the power 5. Now we know in LeetCode C++ specifically, in 1 second we can have 10 raised to the power 6 operations. That is, O of 10 raised to the power 6 will walk under 1 second. So O of 10 raised to the power 5 will also walk under 1 second. So O of n is valid. Now to figure out the maximum time complexity, we need to revisit the time complexity table, right? We had O of n factorial. We need to remember this term. O of 2 raised to the power n, O of n square, O of n log n, O of n, O of log n, and O of 1, right? Now we saw O of n executes under 1 second. Now we need to check for O of n log n. Now maximum value n is 10 raised to the power 5. So log n will be 5. So n log n will be 5 into 10 raised to the power 5, which is smaller than 10 raised to the power 6, right? Which is smaller. So we know n log n will also work under 1 second. So all of this time complexities will be valid. What if we had n square? Clearly we know n square will not work, because n square will give us 10 raised to the power 10 operations, which will be greater than 10 raised to the power 6 that we can have in C++ LeetCode. So this will actually operate under more than 1 second. So the maximum time complexity that we can have is of the order n log n. We can also have O of 10n, right? This will also work. We can also have O of 3n. All of these operations will work, right? At max we can have O of n log n. Now we will discuss 3 methods to solve this problem, right? 3 methods are: first we will use 2stack to solve it. Then we'll modify the first method to solve it under 1 stack, right? And third, my favorite, we'll use recursion. Now talking about individual time and space complexity, 2stack will take a time complexity of O of 3n and space complexity of O of 2n. 1stack will take time complexity of O of 2n, I will discuss after, right? And the space complexity O of n. And for recursion, it will take a time complexity O of n and space complexity O of n. So first we will discuss the method 3, recursion. Now recursion has the most shortest and simplest code, and the best part of recursion is that you don't have to internally think how it is working or what should be the logic behind solving this question. Mostly by using this 3 point, you'll be able to solve mostly any recursive problem. Now first, let's say we're given this problem, right? And we need to delete all the numbers followed by a bigger number. So we delete 2, then 5 is followed by 13. So we delete 5, and then 3 is followed by 8, a bigger number. So we delete 3, and we'll have 13 and 8 as answer, right? Our answer will be 13 and 8. Now internally what node to delete and what should be the logic, we don't have to actually think in recursion. All we'll do is we'll assume the first point is we'll assume the answer. Let's say we have a function named delete node. Now this function, let's assume this function is complete, and if you pass the head, right, in this case head is 5, if you pass the head, it deletes 5, 2 and 3 and it returns you 13 and 8, right? Simple. Now the second step is convert the bigger question into the smaller question, and this is the most important step. What you could do is, instead of passing the whole linked list, you could just simply pass this part of the linked list. 2 is head next, right? What happens if we pass head next into delete node. Let's say we have delete node which deletes all the unnecessary nodes and returns us the answer. And if we pass head next, it will delete 2 and 3 and return us 13 and 8. Simple, right? Now, but this is not the answer, right? This is not the answer. We have to take account of this 5 that we left out. So what we should do is we have to check if the left out node, the head value is bigger or smaller than the returned node value. The returned node value is 30. Let's call it small head, right? It will return some head, right? Let's call it small head. Now, if the head value is less than small head value, what we will do is, if the 5 is smaller than 30, we'll simply delete 5. So simply write it, delete head is 5, right? So we're deleting 5 and we have to return what? Return 13. Now 13 is small head, so we'll return 13. Return small head. But there is another condition we need to keep in mind. What if the starting element is larger? What if we have 20, 2, 13, 3 and 8? Now we assumed a function that does the work, right? Then we break a bigger problem into a smaller chunk. This is the smaller chunk. We pass head next. And the function deletes 2 and 3, returns us 13 and 8. But we have to take account of this 20. Now 20 is bigger than 13. So we'll have to include 20 to 13 and 8. 13 is our small head. 20 is our head. So if head value is greater than small head value, what we will do is we'll attach it, right? We'll do this part. So head next will be small head. And this is our recursive code. We don't have to actually think what node to delete, what to connect. All you have to do is convert a bigger question into a smaller question. We'll have our answer. But there is one step missing, is the base condition, which I will explain. Let's write the code now. Delete node. Now what should be the type of delete node, right? What should be return type? The return type should be list node, right? Because it is returning the head, the small head. So let's say we have this function list node, delete node. And initially what we are doing is, initially we were passing the whole linked list, right? So we'll pass list node head. Now inside it, what we did was we converted a bigger problem. This was the bigger problem, bigger question into a smaller question, and we passed the smaller question's head into the function. So do that. So we called the function delete node. We passed head next inside it, right? Then what we did was the return value of the smaller section of the problem will also return a head. Let's call it small head. So we'll write list node small head. Now let's say we have, let me write the question. We had this, right? Using this statement, we passed this part of the linked list. So it deleted 2 and 3 and returned us 13 and 8. And we are assigning 13 to small head, right? This is small head and this is our head. This is our head, right? Now we need to figure out if the head val is smaller than the small head val or not. If it is smaller, then you have to also remove it, right? This was the bigger problem that we need to return. This is the sub problem, right? So if the head value is smaller than the small head value, we will delete the head and return small head. So our answer will be this, right? We'll return small head, return small head. Now, what if the front node that we had was greater than the small head? Then we'll simply add it to the small head. So we'll write head next will be the small head. Head next will be the small head. And this is our recursive code. Now, at the end, we'll simply return the head because the return type was list node. If the first node, let's say the first node is 20 and the answer returned by the smaller section problem was 13 and 8, then this is the smaller head that we have returned if this is excluded. But if this is included, this is the head that we need to return at the end. So this is our recursive code. But there is one thing missing, that is we have to include the base condition. Now the base condition, we have to include the smallest question possible. We can get an idea from the number of node in the constraint section. We had the number of node from 1 to 10 raised to the power 5. So that minimum number of node that we can have is 1. So this is the smallest question that we can get, is right. We can be given just single node and we need to return. So what we'll return is simply we'll return the head. So the base condition will be figuring out the smallest question from the constraint section. From the constraint section, we know कि we can at least have one node. So we'll simply write if head next equals to null. That simply means that we have only one node. So we'll simply return the head, right? And this is our recursive code. And talking about the time complexity, it runs in O(n) time complexity because we have to at least visit one node once. And for the space complexity, technically it is O(1), but practically internally it is consuming stack space, so it will be of the order O(n). We will discuss the toStack method. In this method, what we do is that we take a stack, right? Let's say st1, and we start from the head, right? We start from the head and keep pushing all the elements. Let's say we encounter 5. Now we push it into the stack 5. Then we are at 2. 2 is smaller than 5, so push it in, right? Then we encounter 13. Now 13 is bigger than both 5 and 2, so we need to actually remove 2 and 5, right? So we'll simply, before pushing 13 into the stack, we will remove 2 and 5 and push 13 inside it, right? Now we have 3. Now 3 is smaller than 13, so we'll keep it, right? Now we are at 8. Now 8 is bigger than 3, so technically we need to remove 3. So before pushing 8 into the stack, we'll remove 3 and we'll push 8 after it. Now currently our stack only has 8 and 13. Now the answer to this question should be 13 and 8. Our stack only has 8 and 13, right? What if I pop all the elements from the stack and create a linked list? Let's say I pop 8 and add a new node and create a node and add a link to it. Then pop 13 and add 13 to it. Now this is our linked list, but this is actually reverse to what we actually want, right? We want 13 and 8 and we have 8 and 13. So to actually reverse this stack, we'll use another stack, push all the element from stack 1 to stack 2. So we'll pop out the 8, push it into the stack 2, pop out the 13, push it into the stack 2. Now we have all the elements in order. Now simply what we will do is, from the stack 2, we'll pop each element out, make a node and keep a chain. Till the stack is empty, we'll keep on creating nodes, and at the end we'll return the head of it. Now simply every single thing that we did is we're going to write in code. First we are going to create a stack. So stack of integer st1, let's say, and we need 2 stacks, so another stack integer st2. What is the first thing that we did was we pushed all the elements which are smaller than the current element, we pushed it in, and if we found a bigger element, we popped all the elements which are smaller than it out of the stack. So list node, let's say temp, we need to iterate over the linked list, right? List node temp head. right? Now we need to run a loop. So while temp not equal to null. Now we are first we have an empty stack, right? First we have an empty stack. Let's say we have some elements 1 2 3, let's say some elements into the stack, and we want to push 4 into it. Now we will check if 4 is larger than the top element of the stack. Now if 4 is larger than top element, we'll pop it out, and we'll keep popping out until the stack is empty, or we encounter a larger element than 4. Let's say we had here a 7. Now we'll pop out 3 and 2, we'll stop at 7 and we'll push 4, right? This is what we were doing. We pushed in 5, we pushed in 2, and as we saw 13, we popped out 5 and 2 and pushed 13 in. So we will first check if the stack is empty or not. So while stack is, let's say if the stack is not empty, so currently stack has some elements, so we have to compare and push it in. So if the temp value, right, if 4 is greater than 3 and greater than 2, we'll pop this element out. So we need to write it down. If temp value is greater than the top element, so st1 dot top, what we will do is we'll simply write st1 dot pop, right? Now this will be our this will be our statement. So we'll pop out 3 and 2. Now as we encounter 7, so 4 is not greater than 7, so we'll break out of the while loop. So our else condition will be else break. So we actually popped out 3 and 2, and our stack has only 7. And now after that we have to push the 4 inside it. So we'll write st1 dot push push what, the temp val, right? Now after that we also have to change the temp, right? Move the temp to the next node. So we'll write temp equals to temp next. Now this much code actually converts 5 to 13 3 8, right? We had 5 2 13 3 8 2, we push the only 13, right? After that we push 8, right? But this is stack 1. Now this is in reverse order. What we have to do is we have to convert this to 8 and 13, right? We have to use stack 2. For this, what we will write is simply while stack 1 is not empty, pop out all the element of stack 1 and put it in stack 2 to make the order of the element correct. So we'll pop out all the element of stack 1 and we'll do st2 dot push st1 dot top, right? And then st1 dot pop. So this part converts the correct order of elements from 8 13 to 13 8. Now what we have to do is, using this, we'll create a linked list, right? We'll first create a 13 node, then we'll create a 8 node and return the head. Create the head of the linked list, list node, new head equals to new, let's say list node, and we will pass the top element st2 dot top, and we have to also pop the top element out as we passed it into a created this, right? So we need to remove it from the stack. So we'll write st2 dot pop. Now what we will do is, let's say the stack 2 had a lots of elements and we only popped the top element and created head, right? Now we have to pop all the other elements. So we will run a loop. The condition in the loop should be key until the stack 2 is not empty. st.2 is not empty. We'll run a loop. Now what we will do is we'll pop the element from the stack, right? Put it in the node and connect it with the head. right? We had the head. Now we also need a mover or a list node. Create a mover pointer so that to connect all of these node and assign it to new head, right? We are simply creating a linked list from the stack. Now we'll create list node, new node. In the new node we'll use new list node st2.top. So the top element gets inserted into a new node. So let's say this is our new node and we have 8. Now this is our new node. Now we have to create this connection. We had this as mover, so we'll do mover next equals to new node, right? So we'll write mover next equals to new node, and now we have to also move the mover, right? We have to move the mover to the next node, so that next time we create another new node, we can connect mover next equals to new node and keep on connecting the chains, right? We will not move the head. In no circumstances you can move the head of a linked list. That's why we are using a new pointer named mover. We'll write mover equals to new node, right? Now this is our code. There is a little mistake. After taking the top element into a new node, we have to also pop it out. So we'll write st2.pop, right? This is our code. So basically what we did was, in the stack 2 we had elements, st2 we had elements. We took each element out, created a new node, right? Initially assigned it as head, then popped each element out, created each of these node and connected it. At the end we have to return head, so we'll simply write return head. Return, this is new head, so we'll write new head, right? So this is our code. And now let's talk about the time complexity. This part, which converts the linked list into a stack, will have a worst time complexity of on. Now this part of the code converts from stack 1 to stack 2, will take another time complexity of on. And at last what we are doing is, from the stack 2 we are converting into a linked list, so this is going to take another time complexity of on. So the total time complexity of this code will be O of 3n, and the space complexity, we are taking 2 stack, so will be O of 2n. If you take account of the new linked list that we are creating, that will be also on, right? Now we'll discuss the method 2 using one stack. Now previously using 2 stack, what we did was we created a linked list, right? We had a linked list. From the linked list we took a stack, deleted all the smaller element after the larger, pushed the larger element in, right? Now the answer should have been 13 and 8, but if we pop out of this stack 1, it will be 8 and 13, so we need to reverse this. So in order to reverse stack 1, we use the stack 2, took all the elements out from the stack 1 to the stack 2, and from stack 2 we created a new linked list, popping all the elements out, creating a node, creating a linked list and passing it as a new head, right? This is what we did. Now using stack 1, the code till stack 1, creation of stack 1 will stay the same. Now we will, in place of using stack 2, we'll use a clever method so that we can directly convert stack 1 to linked list. What we will do is that we'll take the node and add nodes in the reverse way. So basically we'll take the 8, create a node, then after that we'll take 13, and in place of putting 13 after 8, we'll put it before. So it will be 13 like this, and we'll connect it and pass it as a head. Now this code is from our program 1 that we wrote, 2 stack. This iterates over the linked list and puts the values into the stack 1, right? Now after this, what we will do is that our stack 1 had 13 and 8. We'll create a new node. Now we'll name it as new head, let's say. Now list node, new node, new list node, and the top element of the stack, st dot top, st1 dot top. Now we have to also pop it out. So st1 dot pop. Now this is our new head. So we created a new head, and after that, from the second element onwards till the stack is empty, what we will do is that we'll run a loop. So while stack 1 is not empty, we will keep creating the node but put it in the front of the new head. So we'll create a new node. Let's say list node type new node, and put the top element. So the top element now is 13, right? This is our new node. We have to connect it this way. So new node next will be new head. We'll write it down, new node. Okay, so before connecting, we have to also remove it from the stack. So st1 dot pop. Now the connection part, new node, this is the new node. Now new node next will be new head. So new node next equals to new head. After that, what we will do is that we'll move the new head from 8 to 13, as 13 is our new head, right? We could have heads before it. So we every single time we have to move new head, right? So that at the end we can have the last element first. So we will return this linked list, right? So new head is equal to new node, and this is our code, right? This is our code, and after that we'll simply return the new head. Return new head. The only difference between the first and the second code was we are not using any extra stack space. Now talking about the time complexity, conversion from the linked list to a stack can be on at max, and from the stack to the linked list will take a time complexity of on. So the total time complexity will be 2 times on, and a space complexity, if we used only one stack, so will be on, and if you take account of the linked list that you have created, that will be an on.